We are going to calculate the pH of a 0.1 molar sodium acetate solution, and we're given the Ka for acetic acid as 1.8 times 10 to the negative 5. Additionally, although it's not stated here, we can assume that the reaction takes place at 25 degrees Celsius, which becomes important later on in the problem. So the first thing that I like to do before I even write down my governing equation is just to set up the reactions that are occurring in this problem. And this is so that I understand what's acting as a base, what's acting as an acid, really what's happening. So the first thing that's really going to happen is that this sodium acetate is going to dissociate. It's in a solution with water. And so what's going to end up happening is that this aqueous sodium acetate will completely dissociate to form sodium ions and acetate. So now we are still in water, and when this acetate is exposed to water, it's actually going to act as a base because it wants to accept a hydrogen to be in its stable state, which is acetic acid. So I'll write out that reaction. We have our acetate reacting with water. And this acetate is going to accept a hydrogen from water and form acetic acid. And then now that this water molecule has given up a hydrogen, we are going to be left with hydroxide. So this is the reaction that's happening. This second one is really what we're going to be using to solve our problem. So now I'm going to set up the equation that we're going to use. So we're asked to find the pH, and we knew that the pH is equal to the negative log of our concentration of hydronium. Well, in this case, we are producing hydroxide, so we're actually going to use a different form of this equation, which is that the pH is equal to 14 minus the negative log of our concentration of hydroxide formed. So the next thing that I'm going to do is set up another ice table to find our concentration of hydroxide. So I will write out all of our components again. We have acetate, acetic acid, and water is a pure liquid, so this won't be written in our ice table, and hydroxide. So initially, we have no acetic acid and no hydroxide. And we know that we have 0.1 molar acetate. And the reason is because in the problem statement we're told we have 0.1 molar sodium acetate. And sodium acetate will completely dissociate in water. So the concentration of the acetate formed will also be 0.1 molar. So that's how I'm getting that value. Then we have our change in concentration to get to equilibrium. So we're going to add some value of x to produce product, and we're going to do that by subtracting away some value of x from this side, and everything is in a 1-to-1 ratio. And then our equilibrium concentration for acetate becomes 0.1 minus x, and for our acetic acid becomes x, and also x for our hydroxide. So now that we have these values, we're going to do something similar to a problem I previously did a video on where we'll use our K equation to solve for X, because ultimately we need X because we know X is our concentration of hydroxide, and that's going to give us our pH. Well, what's a little bit different here is that we have to use Kb, and Kb is going to equal X squared, because we have an X from each of these, over 0.1 minus X. And we have to use Kb instead of Ka because we know that we're not dealing with acetic acid reacting with water. We're dealing with acetate reacting with water, and acetate acts as a base. So instead of Ka, we need to find what Kb is. And also, just a quick note, what I'm going to do is assume that X is much less than 0.1, and in that way Kb just becomes X squared over 0.1. And we always have to check that this assumption that we made is valid once we do calculate X, but this will make it so much easier to plug in to your calculators to solve for X. So really what we need to do is find what Kb is. And we're going to do that using the relation that Ka times Kb equals Kw. And at 25 degrees Celsius, Kw is going to equal 1 times 10 to the negative 14, which is why I stated earlier we can't assume that this reaction is occurring at 25 degrees Celsius. So we know that Kb is just going to equal Kw over Ka, and I get this equals 5.56 times 10 to the negative 10. So now that we have Kb, we can solve this equation for X. I'll plug in what Kb is. And I end up getting that X, which is our concentration of hydroxide, equals 7.46 times 10 to the negative 6. And I'll definitely note here that our assumption is valid that we made, because we assumed that X was much less than 0.1. Now that we actually solved for X, we see that that is definitely true, and so we can use that assumption. So now that we've calculated what X is, we have our concentration of hydroxide, and we can plug in to our equation. So our pH is going to be 14 minus the negative log of 7.46 times 10 to the negative 6, which equals 8.87.